Dr. Jeffry Cooke.
Thank you, and let me know if you can't hear me. I tend to do this a lot. Okay, so sorry about that. All right, it's great to talk here again. So some of you might not have heard my first talk, so I'll have some references and I'll try to explain the connection. But anyhow, we're going to be talking about solar eclipses, but part two. The first one led us through so what a solar eclipse is, etc., an experiment to show that general relativity, Einstein's general relativity, it helped prove it, which is great. And then, so that was a use for a solar eclipse, and does that sometimes. And this one's going to take it one step farther and explain things about general relativity, perhaps, hopefully. Yes, maybe. This is the slide, and I will say that I carefully chose observations helped support the sun-centric theory, because if you look at those, they help support it, so that's right there. Anyway, we'll move on. Okay, so tonight I'll be observing on this telescope, so I have a long day ahead of me. It'll be all night working. But this is on the summit of Mauna Kea in Hawaii. These are the Keck telescopes. They're 10 meters. Diameter mirror. So the primary mirror of this telescope here is about the size of this room, and the telescope's several stories tall, so it's a big telescope. And we're going to be looking for more of these distant supernovae, and hopefully find them all the way back about, I'll say these are go out to about 12 billion light years of travel time. So the universe was about 10% its age when these supernovae went off. So I'll mention that a bit later. So that's what I'll be working on tonight, assuming the weather is good there as well. Okay, so I'm going to start with some really basic stuff, and this is an atom. Okay, and this is the old school picture of a Johnny Neutron atom, right, or something. So you've got protons and neutrons in the center, and electrons going around them. Now that isn't what an atom looks like, but I think we get a sense of that's the components of an atom. And so one of the things about astronomy is we try to figure out universe, nature, etc. And one of the things that transient astronomy, which I do partially, is we've learned where the elements come from. And that's what I'm going to be talking about. So here is probably your worst nightmare. You probably saw this in your science classroom wall, right? You're like, what is that thing? I don't care. Okay. This is the periodic table of elements, and these are all the elements that exist in the universe. And this is the whole universe, now, way back, always. Okay, these are the elements that exist. And they're just atoms, like I just showed you. And the number here tells you how many protons are in the nucleus. Easy as that. Okay, so if you have more protons, you're a different element. Now, if in a naturally occurring state, you also have that many neutrons and electrons. So that's what we have on this table. And that sounds great. You can line them up. There's properties of why they line up the way they do, etc. But in the early universe, right, as physics explained, like because the universe is expanding right now, in the past it was smaller, right? Because even tomorrow the universe is going to be bigger than it was today, but yesterday it was smaller. And so if you wind that clock back or that movie backwards, the universe gets smaller and smaller and smaller, and at some point it could physically be a dot, right? Now, I won't get into I can explain it more if you like it, but it's every space around us that is smaller, so that is happening everywhere. So the Big Bang is when the universe was very small and it got bigger. Everywhere in the universe just got bigger. So it was all very, very compact. So when it started, physics, if you take it back and explain all the way back to like a fraction of a second, is that right? I don't know, we're working on it, probably, maybe not, right? We could look back 100 years from now and say, what were they thinking, right? But right now, this is where we are, okay? So, but physics can explain it, the physics we know can explain it from there until now. So way back, when the Big Bang started, the universe, all the elements, all the energy of all the atoms is compact, so it's really, really hot. So if something's hot, that means atoms are moving very fast. Okay, so imagine a very compact universe with things moving really fast. Okay, and that's going to be the key here. So when the universe started and expanded, it formed some elements, and it formed hydrogen, which is one proton, helium, and a tiny bit of lithium. That's great. And that's it. And the universe went on. Well, we look around us today, we're made of calcium and iron, and there's water, which we know has, oxygen in it. And, where did all this stuff come from? It came from somewhere. Did it just appear out of nowhere, or what happened? So I'm going to try to explain to you where these things came from. And astronomy tells us where they come from. These are man-made elements. So we're really looking at the naturally occurring elements, okay, up to uranium. All right, so we have the Big Bang. Why were not other elements created? And in short, as I mentioned, it's very hot and the particles are moving very fast. So imagine you're just able to create some particles. The universe is expanding, and as it expands, it cools. And that's the key thing to keep remembering. It gets bigger, it gets colder. It gets bigger, it gets colder. And when it gets colder, things move slower, okay? So early on, it's really compact. Things are moving really fast, so everything's banging into everything else, and you can't put an atom together without it just getting destroyed by another one crashing into it. So you just kind of have a bunch of mess. But at some point, it starts getting cool enough and big enough that you can start, a couple will stick together and they're surviving. They're holding themselves together, and you're making things like helium. Well, once it gets cool enough that you can actually make things heavier, which is like oxygen or something, you'll start making those, but again, they'll get blasted. But once it gets cool enough that you can say, oh, now we're moving slow enough they can survive, you have a problem because one of the particles you're making is called a neutron. Remember, there's one I showed you earlier. Well, a neutron, if it's not in a core, in an atom, it only lives for about 15 minutes. So when the Big Bang started, you've got the clock starts. You got 15 minutes to make everything, okay? And it's just too hot to make these bigger elements. So by the time it cools enough that you can make them, you don't have any neutrons left to make it. So you really end up with just those few elements. So now, how did this stuff get here? Well, we've learned that as stars formed from that hydrogen and helium, big gas clouds of it, they'll collapse and they'll make big gas balls called stars, right? And those stars will live, and inside them they have fusion in the core, and that fusion in the core starts making some other atoms. It turns some hydrogen into more helium, helium into like carbon, nitrogen, oxygen, and you get a few of those elements I showed you, but very few. So then you're making some of those, and that's great, but we've learned through studying stars that explode when they die that you get something called a supernova, and it looks something like this. The star explodes after it dies, and you get this violent explosion, and that's a process when the fusion ends in its core, the core collapses, and I mentioned before it can make a neutron star or a black hole, if you heard from my last talk, and all the material gets ejected into space. And the environment there, that incredible explosion environment, you can make other elements. So elements on that chart are made during that explosion, and they just get spewed into space. So you can imagine a pristine, wonderful universe. This here is another way. You get a star like our sun. It blows up into a giant, red giant or yellow giant, and material is being thrown into space. And then eventually it blows off its shell, and the tiny core in the middle is a little white dwarf, and that kind of radiates the material, ionizes it, and makes a bubble. And you get this wonderful thing called a planetary nebula, and that's ejecting material out into space as well. And it'll look something like this. If you zoom in, this is for dramatic purposes, right? If you zoom in, you see this wonderful, but there's actually things taken from, there's these out there in the universe. This is an image from the Hubble Space Telescope of the Helix Nebula of that type of event that happened, and it's out there. If you get one of your telescopes, you can have a look at that, and it's a really pretty planetary nebula. So these material are out there being ejected into space. So now you had a space that just had hydrogen and helium in the early universe, and all of a sudden you're polluting it with material, other things, carbon and I'm trying to think of things off the top of my head. What are the other elements on the chart? Sulfur and sodium and all these other things are going out there into space. Okay, and so then those are big clouds of gas and dust, and they collapse, and then they make the next generation of stars. So you have like a population. First one is called population 1, which is just hydrogen and helium. Now you have population 2 stars, which is a different generation of stars that have hydrogen and helium and some other elements in them. And then those die and pollute even more. And then you get a third generation of stars, and that's what our sun is. Our sun is a third generation star. So if you look at this table, those were from the Big Bang, those ones in yellow. And if you think about stars burning their cores and they're making elements and those explosions I talked to you about, you can account for pretty much these elements, all these guys, and a couple scattered ones down here that I just was too lazy to put boxes around. Okay, but there's a couple down here that it also makes as well. But you're still left saying, okay, what? We didn't get them all. Where these other ones, these heaviest elements? Where did they come from? And that's been a puzzle. But here's our sun, which we're going to see in wonderful glory. That's the third generation star, right? And, is it a fourth generation or something? No, it's not. It turns out, by theory, at first, we'll go back a couple of decades, they said theoretically, it's going to come from things called kilonova. Okay, that's a weird name. It's not killer nova. Okay, but it's kilonova, meaning it's 1,000. It was coined because they're approximately 1,000 times brighter than a nova, and kilo like kilogram, right? So this is when you have two neutron stars, and you can also have a neutron star in a black hole situation, but you need one neutron star at least, merging together. And just to remind people, if you weren't here last time, when those supernovae explode, all that explosion goes outward, but the core gets compressed inward. And when it happens, you compress that material into the ball of neutrons, just a whole bunch of neutrons. So it could be like 2 or 3 times the mass of our sun in a size of something the size of like Chicago, right? So it's really compact. Or you compress it even further and you make a black hole. But if you have the neutron star, it's a big ball of neutrons, and that's very key for the rest of this talk. You got a lot of neutrons sitting in a big ball, okay? And so you have a neutron star, and if they are orbiting each other and merge, they will rip each other apart as they're orbiting and release a whole bunch of neutrons out into the universe. Those neutrons, some of those will decay or break apart into a proton and electron. And now you have all the makings that you need to make some elements. A whole bunch of neutrons, a whole bunch of electrons, a whole bunch of protons, and you're not in this crazy Big Bang fireball situation, okay? And so we're in a great place to make really heavy elements. Does that happen? Sounds good in theory. I don't know, right? So we go back to our guy, right? Einstein, and this is just from the slide from the last talk, mentioning about how his theory of general relativity explained gravity. And gravity is less of a force and more just warping of space-time. And we talked about how Newton's laws doesn't quite work in some situations, but this theory explains the warping of space. And just to kind of remind some people that might not have been here, here is that situation where you have, say, the Earth, which is something really massive, that's going to warp space around it. So that grid of space around it gets warped just because there's a presence of a massive object. So something that has a lot of mass tweaks the space around it. If it's a neutron star, it has even more mass than this in a smaller area, so it really tweaks the space. So you can imagine it getting really warped, and it warps things around it. All right. And I also mentioned how that warping can bend light, right? You remember this part of the talk, hopefully, if you were here? It can bend light, so on Earth a star will appear where it doesn't seem to be appear. I explained how there was an experiment to test that, if general relativity was right. It would show that during a solar eclipse, stars would normally be in their yellow positions, but because of the warping of space-time, they would appear warped because they're near the sun to be out in a different place. And then when the sun passes by, they return to their positions, and there was a plot showing how that measures up to the theory. Okay, great. So basically, the solar eclipse was used to show that Einstein's theory of warping space works, and we have images I showed you before where if galaxies are lined up behind massive things like clusters of galaxies, they can also warp their appearance. This is actually a curved galaxy, which is a normal-looking galaxy back here somewhere, but the light gets bent around, and it gets this kind of warping ring-shaped, and even crazy warping if you're really lined up well right around that object. Okay, so there's a lot of proof other than this that this is what's happening, and you say, okay, that's great, but if you look at this warped concept, if that's the case, if you take that object and move it around, now you're moving the warping around. And you actually create waves in the warping as you move the thing around. And those are called gravitational waves. And so that's something that Einstein predicted. You would have these waves of space warping, which, what? Right, okay, but you have these waves of space warping going through space. And, okay, right, but is that true? And so it looks something like this. If this will play, let's see. Maybe not. Yes. So there's two objects going and they're warping space as they go around. And as they get closer and closer, they warp it more and more, and those waves get taller and taller. And you can see them getting taller and taller, and they get really high. Once they merge together, now you have one thing just spinning. It's not making waves anymore because it's just one thing spinning. So that's how it is, a computer model of what it would look like, okay? And that's great. So we'd like to know if we can see that, and if we could, it'd be a whole new way of seeing the universe. I mean, since the beginning of time, humans are here on Earth, standing on Earth somewhere, hopefully most of us on Earth, right? And to do astronomy, you look up and you passively just sit there, you wait for light to land here, you have some bucket to collect it like a telescope, and you say, what is this? Let me examine it. What's the universe about? And so you can only understand anything in the universe by just sitting back and waiting for light to come down. And you use light, and that can be all wavelengths of light. It could be radio waves, gamma rays, X-rays. All those are light. You use those to examine the universe. That's what's been done over all time. Okay, you'd love to go out there and crash two stars together as a test. You can't really do it. So you just kind of sit back passively and you watch this stuff coming, right? And that sounds great. But with gravitational waves, it's a whole new dimension. It's like hearing the universe. You can think of it that way. So it does not use light at all. You're measuring something, some waves coming to us. There isn't any light. And you will detect things that you can't see with light. Like a black hole doesn't emit any light, but you can detect a black hole. You can detect it moving. So it would be as if, and this is important because, like, say there was a semi coming down the road, out of control, has no brakes, is coming right for our room here, okay? It's honking its horn, we're gonna crash, right? But everyone in here was deaf, okay? You kind of want to know that semi's coming, right? But if you could hear it, you're like, oh, let's get out of here, right? That hearing is crucial. Things can happen in the universe, say behind something that you can't see it, but you can detect it. You also can prove the existence of gravitational waves. Also, like hearing, which I'll show you in a minute how the gravitational detectors work, hearing, you can't really localize things really accurately, right? I mean, if something crashed outside, you say, well, it happened out over here, but you don't say it happened exactly right there, right? Your ears are good, but they can't localize it to just a pinpoint location. The same with gravitational wave detectors. They'll detect a gravitational wave, but they'll say, hey, it's over here somewhere, okay? What we'd like, and ideally, is to say, well, a gravitational wave happens, we detect it, and that event in particular will emit light as well, and then we turn a telescope, see the light, pinpoint where it is, and study it and say, this is what it is, this is what's happening, here's understand what it is, what exploded, what it did, and what elements it created, etc. Well, if you have neutron stars, as I mentioned, crashing together, they do produce light, and that's what the goal was for us to do. So these are gravitational wave detectors. Two of them are called LIGO, one's called Virgo in Italy. For a long time, we just had these first two, one's in Washington State, one's in Louisiana. And so it's like having two ears. You kind of can say something's over here, and if it detects things, it'll detect things over somewhere in the sky, down here, over here. When a third one came online, now we had 3 ears. Okay, so with 3 ears, you can kind of localize a little better, and it helped a lot. So that was important. And so when a gravitational wave happens, as you saw from that movie, those waves are coming along, and as they come along, they'll come along to Earth. But gravitational waves are space warping. So they just go right through Earth. It's not like something's hitting us. It's just that the space itself is warping. It squishes and stretches like this. So the Earth will squish and stretch and squish and stretch as those waves come through. And that's happening right now all the time. But it's really, really tiny, really tiny. And to show how amazing these things are, which I'll show you, I think, is it the next slide? Yeah. Sorry about the bad resolution. Okay, so how amazing these are is, in short, they're kind of this experiment. You've got a laser, You got a mirror that lets half the light go this way and half the light go that way. They reflect off the two mirrors way out there and way out there, and it comes back. So a pulse of light will go out, bounce, and come back. Go up, bounce that way, and come back. Actually, it'll come back to here, I should say. So they bounce, come back, come to a detector, bounce, come back, and come to a detector. So it just pulses out and pulses back. These two things are placed at known distances. And if you send these pulses, if a gravitational wave came through and one of these lengths gets longer, that one's going to take longer to get back to here. And so you would see those pulses arrive at different times if there's a wave coming through. And that's going to change as they warp, as I was showing you, they kind of go, they wobble. So you say, okay, this is a very accurate thing because this long tube, which was shown in, that picture, these long tubes, so here's where the laser is, and these are little mirrors way at the ends. That's 2.5 miles long of a tube, that's vacuum tube, a mirror way at the other end, and it comes back, so it goes 2.5 miles and back. They can measure if that mirror if that length is stretched so accurately, it's down to 1/10,000th of the diameter of a proton. That is crazy accurate, okay? And they measure if waves are coming through. So you've got to they're very small, but they can measure them. And so, here's an example of that movie again. So these wavelengths are, this is exaggerated, but these wavelengths will come through and they will warp Earth and us, okay, as they come through. So these are gravitational waves, and they're quite powerful. Now, if I go to this next image, it's not going. So here's a snapshot like halfway through when it just merged. And you can see those waves, right, as it's rippling out, and it's bigger amplitude, closer, kind of like taller and skinnier, and then flatter and wider. And that's a signature that they're looking for. And so if you were to draw a line over those, like take a line and you draw it over those humps, all the way over there, you get something like that. Father Sapé might recognize that's his logo for Osgrav. Okay? But what happened was, so I learned today, I didn't know the date, I learned today that the eclipse of 2017 was August 21, 2017. Well, this was 4 days before that, so things are happening in the universe at similar times, right? This was on August 17. Well, firstly, sorry, I'm jumping ahead of myself. So that symbol, or that shape, is what the gravitational waves detect. You can see that signal, right? This is what they're detecting. So as they're monitoring it, they're detecting these waves, and when they see one, it comes through, and this is time. So it'd be like, you see more and more and more, and then gone. More and more, and then gone. And that's what this signal is. It's like over time. It's basically, if you think of this as frequency, or the speed of the pitch of the sound, it's like a lower pitch to higher pitch, lower to high. So that is what's plotted here.
This is the last 3 seconds of the 2015. You hear that?
I think this is what Father was trying to play. Okay. And I don't know how the sounds good it is, but this is what it would be. This is times. This is only 1 second, okay? Can you hear that? That's what a gravitational...
100 seconds of real low, and in the last second, whoop.
So the frequency of those waves coming through, if you convert them to sound waves have frequency, right? And low frequency is low, high frequency is high. If you just transfer it straight into sound, you get that sound. So that's what they would sound like if we could hear gravitational waves. Okay, so what I was getting at, I jumped ahead of myself, is back at the solar eclipse in 2017, 4 days before that, there was an event so the one you heard was two black holes merging, that whoop, whoop. And it's a little bit warm in here, isn't it? Okay, so, but on August 17, 2017, 4 days before that eclipse that a lot of people have seen, it was 11 p.m. at night. My group and I were all trying, always watching the news coming in. We get alerts in real time every few seconds. Something happens. It was 11 p.m. at night. Yes, I work late all the time, but it was 11 p.m. at night, and one of these came in, and we're just like, that just looks unusual. That just looks real, where we had a whole bunch of them that weren't really real. So I contacted a team member. Like they actually texted me at the same time, and we're like, what is this? Is this real? And we're like, this looks real. This looks like the real thing. And it looked like two neutron stars merging. This is the first time that would ever happen. Previous ones, there were black holes merging. And black holes merge are exciting, but they don't produce light. They're not going to produce anything we can detect. There were proof of gravitational waves existed. They proved black holes existed. They won a Nobel Prize in 2017, I believe. But we've never seen them. There was no light. The neutron star signal said there's two neutron stars now merging. There should be light. Now you can actually see what it is. Where is it? What's going on? And so I'm getting everybody around the world to turn their telescopes to this. Actually, one person needed approval. So I said, run over to this guy's house. They go, but it's 1 a.m, he's sleeping. I'm like, wake him up. We got to get this thing. Okay. So, we're just doing crazy, right? So we got everything going. We got telescopes on it. And we observed it, and indeed it was. So this is its signal, and I'll show you a little better later, but it's longer, a signal, that the gravitational wave detectors detected. Also, about 2 seconds later, this is a gamma ray telescope in space. It also detected a gamma ray burst in that general area. And the long theory was these things will also produce gamma ray light. So we're like, oh, it's got the signatures. It looks really good, right? So this is the sound of two neutron stars merging together. Okay, that ding is artistic license. Okay. It's like. That's it. Yeah, I'll do that. I'll do that again. All right. Yeah, so now that our burritos are done, we can go have a look what they are. So it's interesting how this happened just right after that, coincidental, everything's great. So we studied with many, many telescopes, and the beauty or the help that God in the universe did is that it gave us a tiny little area to look on the sky. And the other ones, we had these giant strips in the sky, and that might not look too big to you, but to an astronomer, when you have a telescope, there are millions and millions and millions of things in that little strip, and you're like, good luck finding what that is, because you only have a couple hours to find it before it's gone, okay? And there's even more to that. You have to look at it several times to make sure it's actually changing, whatever. So we had this little, relatively small area that was great. So we looked at it, but if you were to think about what that's like, we were looking for a galaxy that had something brighten and fade in it like that over a couple hours, and that galaxy is in all of these galaxies, okay? And you got a little telescope going around looking for things, okay? Or little field of view. So it's not easy, okay? But we managed to do it. Okay, so, and there's the OSGrav logo, which has that gravitational wave signature I mentioned. Okay, so here's the image of that galaxy that hosted the kilonova, taken with the Hubble Space Telescope. Can you find the kilonova? Okay, but when you watch things over and over, you see them change, and they change, and that little dot changed over time. And then we put other telescopes on there to get spectra, it showed that it was. But here's like a movie to show you basically what happened. Even though it's so far away you can't see this detail, this is what happened. So we have two neutron stars. They're going around each other. You can see them kind of warping space. See, everything gets kind of warped, the view of the stars. And they go around each other, and they get closer and closer, losing energy, and finally they crash together, and they explode into a beautiful kilonova. It ejects out a gamma ray burst, and all this gas and material comes out. And this material, this area, this donut, is where lots of elements are made. Okay? And this is NASA. Okay. So when you look at the spectra over time, this is a spectrum, so this is wavelength like blue to red, only it goes into the infrared, and this is how bright it is. this thing evolves over time and it changes, and as it changes, you get these little wiggles and humps. But the beauty here is that when you learn spectroscopy, these different humps are associated with different elements, and you can see which elements are being made and where and when. And so you can start showing, here's where the elements are made. You also learn a whole bunch of other stuff about the kilonova. Okay, so now we're actually seeing and we're proving that theory that a kilonova happens when two neutron stars merge, and also they're producing some elements. Okay, this isn't forwarding. So when you look at our wonderful table here, now we can kind of assign things to where they're made over time. The blue ones are the Big Bang I was telling you about. Yellow ones are those dying low-mass stars, that big puffy thing that made a ring. Remember that planetary nebula-looking thing? The orange one is from these kilonova, these merging stars. You can see they make all these heavy things like, our favorite silver and platinum and gold, which is the title of this talk in a sense. Things everyone uses like thorium. I don't know. I mean, there's all kinds of elements here that are made during a kilonova. Now, do they get everything? Not quite. There's still some mysteries, as always, right? But you're getting most things, almost everything made. And there are some other things. And importantly, these exploding white dwarfs are also what Brenda studies, right? Like a type 1a supernova explosion. They're creating a lot of these other elements, etc. The exploding massive stars with the supernova I showed you that exploded in that wonderful explosion, etc. So they're all assigned to something. But when we look at that wonderful whoop sound and the ding, your burrito's done, right? It told us something really interesting that we never knew or wanted to test. And that's, we know the speed of light very accurately, and we knew there was a theory of gravitational waves which we're proving that we're detecting, but we just didn't know how fast gravitational waves traveled. Do they travel through space instantly? Obviously not. They're waves. They kind of come and go as they pass by. Do they travel the speed of light? Do they travel slower? You don't know. But if you think about it, when the gravitational wave went off, you got a pulse from the gravitational wave and also from that gamma ray burst, which is light. And that gamma ray burst landed about 1.7 seconds later. So either, and this is over the universe of 130 million light years something away. This object is 130 million light years away. For reference, a light year is 6 trillion miles. So 6 trillion miles times 130 million, big, okay? So it's really far away, and over that whole distance, they arrived that close within like a second and a half. So pretty much same speed, right? And if the gamma ray was created maybe 2 seconds after the explosion of the wave, then that all makes sense. They're the same speed. Okay, so that's really cool. So there's a lot of firsts with this event. We have a gravitational wave signal and a light signal were first detected from the same source. We can actually say, look, gravitational waves are real. There's one. That's what it looks like. Here's what it does. Okay, that's really cool. We also have proof that these neutron star mergers produce these gamma ray bursts. This was a 50-year-old mystery, but now we're saying they do. We also confirmed that they make a kilonova, which was that explosion and that dusty ring thing. That was always a theory as well. And one thing, kudos to the theorists. I'm an observer, so, observers and theorists. But the theorists they came up with a model of what this should look like, and you're like, yeah, okay, it looks great, sounds good. But when it happened, it was like almost exactly that model. You're like, wow, that was pretty impressive. So they got that. We know what a kilonova looks like, so now we say, we'll look for more, right? We know what we'll look for. But from this explosion, though, and this is a little beyond this talk, but you can also better understand what neutron stars are, what's their insides. That's really crazy physics there. Where you get something so compact like that. Imagine, 3 times the sun's matter packed in this little ball. Physics gets weird, okay? It's just a weird thing. So this helps you understand that. We also can use these things to measure the expansion rate of the universe. We know that the universe is expanding. This is a new way to do that, which is really cool. As I just mentioned, the speed of gravitational waves is the speed of light, and we better understand how and where these heavy elements are made. So that's from all those elements on the chart, including gold, which we all love, right? Okay, so that's that talk about the gravitational wave part. Thank you. So it's beautifully sunny outside, and you know, when we see the eclipse, here are a few things to think about, okay? Now, everyone's probably been online, learned everything. I'm going to say stuff you already know, but I'll just say a couple things, maybe you don't, or just to repeat, okay? These are just some things. Because when it happens, it's going to be 4 minutes, but 4 minutes goes by really fast when you're something like that. You're just like, oh my God, you know, so if you can kind of have presence of mind and maybe look around for a minute or listen, or, you know, just you have to have that kind of moment, okay? So firstly, this is, you know, what you'll see. As we know, you know, the moon starts to cover the sun, and over some many minutes later, it's slowly moving. Then it fully covers the sun, so it blocks out the main part of the light that we see with our eyes, but then we start seeing things that are more filamentary, which is the corona here, and actually the chromosphere is this little area here. Those things are there, it's just that this part is so bright. Normally there's like a filter on right here. This part is usually so bright it just outshines them, you just don't see it. Okay, but once you block it out, you can see that fine structure, which will be really cool to see. So you'll notice that the temperature will drop, which is pretty cool. Not that we need it to be any colder, but you know, so it'll drop a little bit. People have said different things about animals and insects. I mean, it is a short time, it doesn't give them much time to react. But when I told you about Trumpler's expedition to Australia, about doing the solar eclipse, if anyone knows anything about Western Australia, there are a lot of flies in Western Australia. Like anybody interviewed, they're talking, there's just flies, you know, you're like, okay. So there are a lot of flies in Western Australia, but apparently when the eclipse came, they all just kind of landed. He's like, that's really weird. So we'll see if that happens, if there are flies out there. But maybe birds will do something different or whatever. And if you look, if there's a tree or bush near you where it's making a shadow, you know, just sun going through that, you'll see like the mottled light on the ground. If the leaves are close together, that acts like as a pinhole camera, so you'll see lots of images of the eclipse on the ground, which is kind of cool. So you can do that like while it's getting chopped away, right? You see little crescents of the sun. And you can see the eclipse that way, so that's pretty cool. All right, you can watch for that. And then there's these things called, you know, shadow snakes or bands. And I don't have a sheet or anything, but maybe if we do lay that out, apparently, I haven't seen it, when there's an eclipse, you'll get these like waves of dark and light on a white sheet. And it's not really understood what that is, but it could be the fact that the sun went from a size, like a circle, you know, a size, down to almost like a point of light. And so that when that light goes through the atmosphere, and the atmosphere is turbulent, it can kind of wiggle around maybe. I don't know. You know, it's anyone's guess. Maybe there's probably somebody who understands it better than me. But if we do lay something out, or maybe even look at the pavement, we might be able to see something like that. If you think about it to look down, okay, you know, when it's happening. Some terms that you'll hear and probably know, one's called the diamond ring, which is when the moon's almost covered, but a little bit of the sun shining, so it kind of looks like a diamond ring, right? That's kind of cool. At this point, though, if you think of it, I'm going to try to certainly think of it, because you get two chances, right? You get it there, and then when it starts passing too far, it'll pop up on the other side, okay? When that happens, check your shadow if you can. Like if you're standing somewhere where you can see your shadow, because the sun, again, normally has a size, and so you probably don't think of this very much, but when you look down, you see your shadow, but it's kind of got like a little blurry edge. Your shadows aren't like crisp normally. Like if you walk out now, you look at your shadow, you say, oh, there's my shadow, but it's kind of fuzzy around the edges. That's because the sunlight's coming from a disk, and it's shining at you from different directions, and it kind of fuzzes out your edge. But when it's in this position, it's a tiny little dot of a sun. It's still pretty bright, surprisingly. Like even now, it's just starting to get dark. I mean, you really have to cover a lot of the sun for us to notice, which is you're going to see too. But once you get to this point, you got a little tiny dot of a sun, and if you look down, you have a very crisp shadow. You can even see your hair, like, focused. Okay, so so if you get a chance, that should be pretty cool. I know, a lot to do in 4 minutes, right? Okay, exactly. This is called Bailey's beads, and when it's fully covered, depending on the size of the sun compared to where it's in its orbit, remember how if it's closer, the moon's bigger, if the moon's farther, it's smaller. I think we're going to cover it completely if it's 4 minutes, so you'll see little areas of light, and that's because, why? Craters on the moon, that's right. It's not a smooth surface. If you have a rough edge, you're going to get light popping out, right? And I think you'll have your H-alpha going. Okay, if you do, check that out. Again, get in line and move fast. Okay. But you'll see the edge, and you can see those prominences and things really nicely because you've got the sun blocked out, right? So you can see something really cool. So, we're going to all be busy. Okay. And this is just it evolving over time as the moon's moving. Okay, and clear skies. Thanks.
We do have some time. Dr. Cooke, would you like to take any questions, sir?
Absolutely.
When you talk about
Yeah.
Nice and loud.
when you talk about the universe expanding,
Mm-hmm.
does that mean galaxies going farther apart? Does it mean solar systems going farther apart? Does it mean planets within solar systems going farther apart?
The question is, when we talk about expanding universe, does that mean galaxies are getting farther apart? Inside those galaxies, are they getting farther apart? Are solar systems getting farther apart? Do planets get farther apart? And the answer to that is, space is expanding. Galaxies do get farther apart if they're not gravitationally bound to something. But anything that's gravitationally bound, like a galaxy or a solar system, that gravitational binding is stronger than the expansion. So space is expanding, but they still maintain their size. So a galaxy is going to keep itself bound. If it doesn't have enough gravity, which some don't, they do come apart because it's not bound, especially early universe. But the universe is just space. Imagine that grid of space. It's just that space getting bigger. So everything in it, if it's at some grid point, is just going to move with that grid point. I mean, it's not moving, but that grid point is going to, like if you're 2 points, one will get farther because that grid's getting bigger. So things that are far apart will move away. They are affected by gravity, so they'll kind of want to pull toward each other so that it does change the overall picture of what you're looking at. But everything is getting bigger, and that is dominant in many cases, especially when you look on the largest scales. That's the dominant expansion. But things that are bound, like we'll see galaxies that actually move toward another galaxy because it's crashing into a galaxy, or something gets pulled in by gravity. So you'll see mix of events, of cases. But yeah, in short, if it's bound, it's going to be strong against that expansion.
So I guess just like a follow-up to that, does that mean that galaxies do not rotate around anything?
Well, they're rotating around like a common center, right? I mean, because they're gravitationally bound, and as particles fall in, they kind of like fall, like say you're falling in, but you don't fall, everything doesn't fall right exactly to the center. If you miss a little bit, then you'll come back around and you kind of circular way in, and everything just starts to rotate, and it's all rotating about a point in space.
Within the galaxy.
Yeah, so there's a point in that galaxy that's like the center.
But I mean the entire galaxy.
Yeah.
Is that rotating around?
Oh, sorry. So there are galaxies that are moving around a common center of groups of galaxies or clusters of galaxies, because you've got that gravitation, extending. It goes on to infinity, but gets weaker. Yeah.
So in that sense, a galaxy is gravitationally bound around?
Yeah. It can be. Yeah. I mean, galaxies that, if they're very sparse and very far apart, then they're just kind of floating out with the Hubble flow, or the expansion of the universe. You have, yeah.
So you talked a lot about the gravitational waves. I found that fascinating. And you did say that you think that the gravitational waves are moving about the same speed as light. And you also talked about like how pretty much as soon as you got that wave, you started moving telescopes around. How long of a time frame is that between getting that first signal from the gravitational waves and having that light be almost like not relevant anymore?
Very good question. The question is, I'll just say it briefly, summarize it. When the gravitational waves came and we were detecting the light, they travel about the same speed, but how long after that happened is it relevant to be detecting this light, I guess is a short way of saying that. And that is, in this case, it depends on the kilonova, it depends on which wavelength you're looking at. So if you're looking like optical, like our eyes see, and if it's more if you imagine a rainbow, if it's the blue end of that, you've got about 2 days. So you have some time. It rises in several hours, and it fades in a couple of days, depending on how faint you want to consider fade. And so you got about a day or two to do that. And then for redder wavelengths, it might be 4 days or something. Okay, so you have some time. And then if you're in the infrared, you might have up to 2 weeks. So you have some time. The problem, though, is if you're trying to find it in the optical, which is usually what is done, because the optical telescopes have the biggest field of view, you're trying to look at this giant area of the sky. You have a short amount of time, as I mentioned. However, you only can look at night. So if you have a day and a half or something, you got like 1 night, maybe 2 nights. Okay, that's fine. And then where is it? If it's over there, and you say, well, in an hour it's going to set, you only have an hour that you can look at it before it sets. You're like, okay. So you get really constrained on how you can actually find it, but you do have time. It's just not a lot of time. You have to image that whole area I was showing you. Then you have to image it again. Did anything change? Then you have to image it again. Did anything? So it takes some time. Yeah. How about in the back? I'll come to you. Okay.
The gravitational waves, do they use some sort of discernible energy, and does it dissipate over time?
They dissipate. So it's energy. It's space. So it's gonna be like an energy density, and it'll dissipate as it goes out.
It doesn't go on forever.
It doesn't. Well, it fades and fades. Yeah.
And do they interact?
Yes. Do.
In the same.
And just say again.
Like in the same sense as water?
Yeah, in the sense. So there's an experiment that looks at pulsars around the sky, which are neutron stars, as I mentioned. These are terms. And sorry, but they're neutron stars that spin really fast, and they have a beam of light in the radio, and if it's spinning, if that beam of light is off axis, it kind of spins like this really fast, a few times a second. And if we happen to be aligned, it'll swoop by us. You say, "Oh, I see a flash. I see a flash." Okay, they're really well timed, and so they just spin really accurately. But they're measuring them, and if they measure them all really accurately, you can see that sometimes some will arrive a little bit later than others because the gravitational waves are affecting that. It's interesting.
Dr. Cooke, when all these scientists get the results, you publish your paper, and names go on that paper. Chief author. What number author of that paper are you?
I don't know, because this was a paper that had 3,780 authors, I think. I'm probably like 3,002. I don't know, because they so many. They just said, well, here are just groups of people that contributed. So here's this group, and here's this. What do you do at that point? Of the main one, of the one that we wrote, exactly. Okay, so there's a main paper that I was referring to, which is like the LIGO Virgo official. Here's the announcement of everything, big paper. Okay, that has a gazillion authors. The work that I did, where I coordinated 15 telescopes, actually would have been the first author, because you do whatever. But I had a student, and I'm like, he needs a good career. He did most of the work. Here, you be first author, because he did a lot of the work, most of the work. So he was first author, and then another postdoc was working. So I ended up being third. I'm good. Get a question real quick? Okay.
Any other questions?
Is there a Nobel Prize for this?
There was one for the detection of the black holes merging, and that was in 2017. So there's a Nobel Prize for that. Don't think they'll probably do another one for neutron stars. Maybe could happen. I don't know. Yeah. Okay. Yes.
So I noticed when you were showing the graph that shows the different elements being produced, and it had a time going on, so I'm watching the time going. So it was like 10 seconds.
Oh, yeah.
The change in 10 seconds.
Yeah, the spectrum.
So
Yeah.
I liked that was on there, so you could see the spectrographic data.
Yep.
So, but you have sort of a dramatization of the kilonova.
Yes.
So that,
Yes.
what's the time frame on that?
Okay, good question. So the question is, I showed you that wonderful, pretty movie of the kilonova exploding, and then I also showed you a spectrum where it was like, you saw this like plot of a wiggly curve that kind of changed over time really slow. How do they connect time-wise? That explosion movie, I don't know if everything's accurate on it, but it's close. It's fast. It's probably just hours to a day total on that movie, maybe hours. Is that it? And then the spectrum was like 1 day, 2 day, 3 day, 4 day, so much different progression. So that dust ring that was formed moved outward, cooled, more dust formed, and then radiated, et cetera. So a lot of stuff happened beyond that pretty pink cloud of picture. Yeah, if that helps.
Yes.
Yeah, good. Yeah, the gamma ray that you saw like a jet come out. Like when it exploded, there were these jets coming out. That's fast. Yes.
Well,
Well, they're, yeah.
So do neutrinos come from neutron stars, especially like in a kilonova, which is some more neutrinos, or?
Neutrinos, do neutrinos come from kilonova? Yes, they do. And when a neutron decays, it's called beta decay, it can break into a proton and electron, and a neutrino comes out of that. And so all those neutrinos will be flying out. And those, yeah, you try to detect those as well. Yep. You had a question or no?
Yeah. Looking at the sun when it's starting the eclipse, when you keep looking at it, I mean, that's not a problem for your eye.
So the question is, if you keep looking at the sun during eclipse, is it a problem for your eyes? And the answer is, don't look at the sun ever, right, for a long period of time. You can glance at it. And as it's getting eaten away, have those glasses on. Technically, when it's fully covered, you could look with your eyes, and you probably should. It's, safe, but, I'm being recorded, okay. but you should be able to take off the glasses, look at it. You want to see it in all its glory because the sun's light's mostly blocked. Okay.
I'm worried about missing it. I'm not going to miss it.
You're not going to miss it.
Okay.
So once it gets closer, you just kind of go, okay, yes.
No, just a basic question. Is it true that nothing is faster than the speed of light?
The question is it true that nothing's faster than the speed of light? And that is yes, except theoretically there are things called tachyons and stuff like that. But light is more the speed of causality, so when something happens. And so that's an entire talk in itself, but light is more a limit to how fast something can propagate through the universe. Let's put it that way, yeah. Yes?
I heard that they developed a quantum calculator. You know anything about it? Because it seems like it's operating faster than the speed of light, communicating information.
So questions about a quantum calculator or computer, and does it communicate faster than the speed of light? It doesn't. It's entanglement of, this is out of my area, but it's entanglement of atoms. So once they're entangled, then once you see one, you can find it, the other one appears in its state. It's not that the information is communicated fast enough. It's always had that information in a sense. Well, again, another entire talk, okay? And people have their different opinions on that, but in short, I would say it's not communicating faster than the speed of light, even though the information can be learned from one place to the other, seemingly faster than the speed of light.